Hi, my name is Yoshinori Matsunobu. So I'm a production database engineer at Facebook. So today I'm going to talk about the story about how we migrated from traditional MySQL InnoDB database to our new database MySQL engine called MyRocks. So why we created that and how we migrated in production. So let me briefly introduce myself. So I used MySQL for over 10 years. So I was a MySQL consultant at MySQL company, which was acquired by Sun in 2008 and was acquired by Oracle after that. So I worked there for nearly 4 years. And I joined Facebook about 5 years ago. And I mostly spent time for MySQL deployment, production engineering side. So like a MySQL 5.1 to 5.6 upgrade, and MySQL failover on the master crash without losing data. And I partly joined the HBase production team about 3 years ago. I learned a lot about how difficult HBase is and what parts are great. And I learned that the log structured merge database is pretty good for saving space. So I came back to a MySQL team and started a research project to integrate the log structured merge database, RocksDB, and MySQL. So integrating RocksDB into MySQL project, we started with our Facebook database engineering team about 3 years ago. And finally, we created that, and we started deploying in production since last year. So today, I'm going to talk about these. So MySQL at Facebook and issues that we faced in traditional InnoDB database in MySQL, and the RocksDB and MyRocks overview, and how we deployed in production. So main MySQL database at Facebook. So Facebook is a huge MySQL customers, one of the largest MySQL customers across the world. So we heavily use MySQL as a main database. So we store social graphs. For example, if you click likes or make comments or share somebody's post, then all of these activities are stored in MySQL database. And mostly we still use InnoDB, so transactional database engine. And it's massively sharded. So apparently, single MySQL database is not enough to serve billions of Facebook people's social data. So we massively sharded. And MySQL database itself doesn't support shard. So we created an application that, so from application side, we are sharding aware and distributing data across multiple databases. And it's petabyte scale. So it's not just terabytes, but it's smaller than the data warehousing, which is 100 petabyte scale, but it's still pretty large. So it's not just a small data, so handling a petabytes data scale. And low latency. So when people access to Facebook, the news feed is shown on the user's web browsers. And in most of the cases, we have the application's request hitting cache. So we have a huge cache in front of MySQL, which is called tau, which is a huge record cache. So in most cases, the read request hitting cache. But if cache misses, then user's read request go to MySQL database. So the select statements have to be handled. And if it takes time, then it affects the user's experiences. So it is very important to handle queries within short range. So typically, our main MySQL database query, the processing speed is about 1 millisecond, or even less. And automated operations, so we have about 10 to 15 people working on MySQL production deployment. So apparently, this is quite small to handle a lot of MySQL databases. So we automated most of the operations. Like backups, or if MySQL server is crashed, or if MySQL server is having problems, then our automation daemons automatically detect that and schedule to reimage, then allocating a new server to handling the MySQL workloads. For example, if the MySQL replication slave is died, then it is reimaged, and automatically it assigns the new machines for handling of new slave workloads. And we use pure flash, the flash storage, so not hard disk drive. So there are some exceptional use cases for handling using hard disk drive, but on main databases, so we use pure flash. So pure flash is very fast, and the workloads, the read and write IPS is pretty fast. But one big limitation is it is more expensive, so much more expensive than hard disk drive. And the flash has a write endurance. So if you write hundreds of megabytes per second to flash, then flash card will burn out. So it is also important to write less to flash so that you can use the same flash devices long enough. So from utilizing MySQL database on flash, so there are several issues in the traditional InnoDB database. So we heavily invested in the InnoDB for a couple of years, but to utilize on flash, there are a couple of issues. So one is a write amplification. So this is a brief image of how InnoDB works when handling writes. So when modifying one record of the table, then first the MySQL database reads the 16 kilobyte InnoDB page into memory. Then modifying one record, then writing the entire page to storage. So this is a traditional workload of the B+Tree index. So the problem is, so even though you just modify 1 byte or 1 record, then entire the 16 kilobyte page becomes dirty. So you have to write 16 kilobyte page to storage regardless of the modification of the bytes. So even though you just modify 1 byte or 2 bytes, the entire 16 kilobyte page has to be written to storage. And InnoDB also supports page corruption, the prevention feature called a double write. So it is important to use this feature to protect data on unscheduled machine failures. So this doubles the write volume. So in total, so you need to write 2 pages to storage. So if you don't use InnoDB compression, then the total bytes written is 32 kilobytes, which is pretty large compared to modified bytes. So it is pretty common that write amplification, so the written bytes to storage compared to modified actual bytes of the logical modification bytes, is typically like 1,000 or 100 or 1,000 or even more. So it is pretty high in InnoDB. Another issue is fragmentation. So fragmentation is a common issue for the B+Tree index. So this is a brief image of how B+Tree pages are fragmented when inserting in random order. So suppose there is a message table. So message table keyed by a secondary index called the user ID. So user ID is inserted pretty randomly into this index. And this is in this leaf page, up to 60 user IDs are stored in this single page. And trying to insert the 31. Then there is no space to insert 31. So in that case, the page is split into 2. So up to 30 and 31 to 60. Then about half page becomes empty to allocate more data. But almost half page becomes empty, but it still uses the space. So in this case, the page size gets doubled. So it just uses additional page to serve data. So typically, it is pretty common to use 50% or even more space just for the empty data, so which is unnecessarily increasing space. So the B+Tree index fragmentation increases space, which is not so good when using on Flash. The third issue is InnoDB compression. So not many relational databases support compression, but InnoDB is pretty good for that it supported compression about nearly 10 years ago. So we heavily invested in InnoDB compression, and we use it in main database at Facebook. But here's one big issue in InnoDB compression. So this is a brief image. The original uncompressed page was 16 kilobyte, and the page was compressed to a 5 kilobyte after compression. But logically, so on the space side, it still uses 8 kilobyte. Why? Because in InnoDB, so you need to specify after compressed page size. So after compressed page size is normally you set to 8 kilobyte compared to 16 kilobyte page. So this means, so even though you could say compress less than 8 kilobyte, it still uses 8 kilobyte. So this is called InnoDB page alignment issues. So this means so you cannot save space more than 50% because the page is always more than 8 kilobyte. So this is a common issue in InnoDB. So by combining with the InnoDB fragmentation and the compression alignment issues, so it's pretty common to use more than double space than necessary. So that's why we started researching different database solutions, different database architecture to save space on our main database. And that's why I joined HBase team a couple of years ago, but unfortunately, we decided the HBase was not the right choice to replace InnoDB. But we found that the LSM database architecture was pretty good to save space. So instead, we looked into another database called RocksDB. So RocksDB is an open source log structure merge database. Currently, it's developed by Facebook. So originally, it was created by Google, named LevelDB. LevelDB was also open sourced, and it's created by Google. And we forked that and developed RocksDB for our background, the major backend services. So LevelDB and RocksDB are key value, the LSM persistent stores, and it's embedded. So and the data is stored locally, and it's pretty efficient. So it's pretty fast and optimized for fast storage, the flash storage. So yeah, as I said before, so we use RocksDB at many backend services at Facebook, and many external large companies like Netflix are using RocksDB. So one big limitation of RocksDB is, so this is just a key value store, the NoSQL. So you need to write a C++ or Java code to access RocksDB. So it's not for everyone. So you can use it if you can write a code, but the limitation is pretty strict. So this is how LSM and RocksDB works. So suppose there is a message table, and inserting into the table is random order the user IDs. Then the user IDs randomly is inserted into a read log called write-ahead log, and the buffers, it is called, there is a mem table for accepting writes. So when mem table gets full, then the new data file is written, called flash. Then the new data file called SST file, the sorted string table file is created. And when there are many SST files created, then another process called compaction happens to merge multiple SST files, then reading multiple SST files, then writing the new SST files with more optimal format by sorting data and using a stronger compression algorithm. So these are called compactions. So the flash, the mem table flash, sorts the data and writing to SST file with compressed format, which is significantly saves space. And another compaction happens, periodically happening, and saving space even more. So by combining these steps, the fragmentation overhead and the compression alignment overhead is pretty small. So typically, the RocksDB's the space overhead is only 10% compared to the original data. And InnoDB's overhead was more than 2x. So by comparing RocksDB and InnoDB, even though you're just using the same data, the InnoDB space is more than doubled compared to RocksDB. So after researching the couple of RocksDB options, so it greatly saved space. So we started to look into RocksDB more. So we wanted to use RocksDB in our main database. But one big limitation of the RocksDB is you need to write a C++ or Java code to access to RocksDB. And existing MySQL customers, so InnoDB customers, are using SQL to access to a MySQL database. So rewriting all SQL applications to a RocksDB specific API was pretty painful. So that's why we decided to integrate RocksDB into MySQL. So this is a project called MyRocks. So MySQL has an architecture called a pluggable storage engine. So InnoDB is technically, so InnoDB is also actually a NoSQL database. And MySQL integrated that. InnoDB and MySQL integrated, and people access to InnoDB almost by default. And we did the same thing for RocksDB. So we integrated the RocksDB into MySQL by supporting multiple APIs in MySQL, which is called a storage engine API. So we, by doing so, then MySQL clients can connect to MySQL in traditional MySQL command line script or MySQL the connector programs. Then accessing to RocksDB database by regular SQL commands, like select or insert. So traditional SQL statements can access to RocksDB. So by doing so, you don't have to modify applications in theory. So by which is mostly a drop-in replacement. So by just switching the backend InnoDB database to MySQL MyRocks, then applications can transparently access to a MyRocks database without changing anything. So MyRocks is also open source. There's a homepage called myrocks.io, and this is a QR code. So if you are interested, then feel free to check out and try. And which is open source, and it's also distributed from MariaDB and Percona, which are the major MySQL distributors. So both companies support MyRocks. So yeah. So MyRocks goals at Facebook. So this is a common kind of brief environment of our main database. So our main database is space-bound. So it's about, there is a machine limit, and almost 90% of the space is used. And about 20% CPU is used, and the I/O is pretty low. So both CPU and I/O are fine, but the space is very limited. What we are trying to do with MyRocks is, so by switching to MyRocks, saving space. So this was the major goal. So the CPU and I/O are pretty comparable. So we tuned a lot to handle pretty well. But it doesn't matter very much because there are plenty of space. Space is the matter. So by switching to MyRocks and saving space, so this was one part of our goal. And the second goal is adding additional instance to the same machine. So adding additional instance to the same machine means so the machine gets a double workload. So using more CPUs and using more I/Os, and the space is so double, so it's 90% in total. So traditional log structure merge database was not so good for handling I/O and the CPUs. So this was a big limitation for us. So we evaluated other databases like TalkDB, but in that case, the CPU utilization was so high, so we couldn't consolidate two instances. But with MyRocks, so we tuned a lot to save CPU and I/O. So this was pretty feasible to consolidate the two instances into the same machine. So this was our major goal of the MyRocks deployment, and this is what we are doing in production. So more details. So smaller space usage, so 50% compared to a compressed InnoDB at Facebook, and the better write amplification. So better write amplification means so you can use the same flash longer, or you can use more affordable flash. So instead of purchasing a expensive flash. And fast and a small enough CPU usage with general purpose workloads, like a large enough data that don't fit in memory, which is typically for our main database, and doing a pointer lookups or range scans. For example, if you get the people's post, then you can see who likes the post. So this is internally, so we do a range scan to getting a list of people's IDs who liked that specific post. So we do a range scan, and we do pointer lookups, and occasionally we do a bulk full table scan or full index scans for backups. And we do insert or update or delete by pointer and range. And we occasionally do bulk inserts for migrations or schema changes. So for these workloads, so we need to use the same or even smaller CPU usage compared to InnoDB so that we could consolidate more instances. And so finally, so we made it possible to consolidate 2x more instances per machine. So we tried to match InnoDB. So we added pretty similar or comparable features compared to InnoDB. So our index structure is same as InnoDB, so which is clustered index. And we support Bloom filter to handle reads more efficiently. And we support transactions, so including consistency between binary logs and RocksDB, which is pretty important for our consistency guarantees on machine crash. And we supported fast data loading or deletes or replication. And we can change most of the RocksDB configurations without restarting MySQL database. And we also supported TTL. So TTL is a feature of the HBase. So the deleting all the data without running any scheduling jobs. So automatically purging data when hitting the specific time, which is pretty good for time series database. And we also supported online logical and binary backups. So we added several features so that we could run in my main MySQL database. So before talking about the production deployment, so let me talk about our Facebook MySQL related teams. So we have a production engineering team and a software engineering team that does the RocksDB and MySQL deployment engineering. So I'm part of the PE, the production engineering team, which consists of MySQL production engineering, so automating MySQL and finding bugs in MySQL. And also there is a data performance team, which is finding performance problems of the MySQL and finding longer term plans to make MySQL better. And we have software engineering team, which is maintains and develops the RocksDB code base and the MySQL code base. And the MySQL engineering team has MyRocks team and others. So MyRocks team is making MyRocks better, and the others team do other MySQL features like a replication or client or InnoDB. So relationships between MySQL PE and SWE, so software engineering, is not that strictly separated. So for example, software engineering of the MySQL team does MySQL server upgrade because software engineering, MySQL engineering team creating a new RPM, the MySQL packaging, then upgrading MySQL version with several patches. And sometimes we need a hotfix to fix some urgent bugs. So the SWE team creates that, then deploying that in production. And software engineering team also participates in production engineering on-calls. For example, the investigating issues together that might have been caused by MySQL server code base. Then we need urgent help from our software engineering team. So very often, so we investigate issues together and fixing bugs. And actually, we can submit diffs each other. So our automation tool, the PE tools asset in Python mostly, and MySQL code base is C++. So it's different, but anyway, so it's not strictly prohibited. So the PE can write a MySQL diffs and submit a diff, and the MySQL engineering team can review that. And MySQL engineering team can submit a Python MySQL automation diffs, and MySQL PE can review and accept that. So we have a concept of a hacker week to participate in the different team. For example, MySQL engineering team members can join 1 week for MySQL production team and doing some automation stuff to making things better, to understand better for what they are doing each other. So this has been working pretty well so far. So from this slide, so let me talk about how we migrated our main database from InnoDB to MyRocks. So there are technical challenges when migrating the main database, because main database is very critical. So if there are huge problems, then it will result in a Facebook site outage, which is critical. So we spent a lot of time to evaluate if it is safe to migrate. So initial migration pain points are creating a MyRocks instance without downtime. So there are existing InnoDB instances, and how we can create MyRocks instance without downtime. And we have already the petabyte scale data, so how to load from InnoDB database to MyRocks database within reasonable time is another pain point. And after loading the data, how to verify the data is consistent between InnoDB and MyRocks. This is another big point to guarantee that. And the continuous monitoring, like a resource usage, like a space, I/O, and CPU and memory, are important. And the query plan outliers or stores and crashes. So continuous monitoring is important. And the typical, it's MyRocks specific challenges is how to run MyRocks on master database. So master database serves write traffic. So it's much harder than running on slaves. So slaves serving read traffic, and the master serving write traffic. So running MyRocks on master is much harder than running MyRocks on slaves. So running on master needed additional verifications. For example, MyRocks doesn't support the statement-based binary logging in MySQL. So we switched to a row-based binary log to make it work. And MyRocks has some features. MyRocks doesn't support several features that InnoDB does. One most significant feature is called a gap lock, which is a range. So InnoDB has a feature to lock the range of the record, like a greater than 10 means select from a table where ID greater than 10 does the locking all records greater than 10 and preventing any users from inserting into the value with ID greater than 10. So MyRocks doesn't support that. So we removed queries relying on the gap lock, the range lock features. So the first, we created the first MyRocks instance without downtime. So this was relatively simple. So if you are familiar with MySQL, so you can imagine that this is not so hard. So what we did was picking one of the InnoDB slave instance, then starting logical dump and restore. So we use pretty typical MySQL replication architectures. So MySQL master and slaves. So master was InnoDB and the slaves was InnoDB, and there were multiple slave instances. So by stopping one of the slaves, then dumping and loading into another instance with MyRocks. So this was a single step, pretty simple step to loading from a InnoDB to MyRocks. So another issue is how to create MyRocks database within reasonable time. So normal write path in MyRocks and RocksDB is pretty complex. So when issuing a write request, then first write request was written to a write log, which is a transactional log. Then the data is written to a mem table, when memory table gets filled, then it's flashed to a level 0 SSD files. Then another compaction happens to level 1, 2, 3, and max. So even though you just write 1 byte or 2, then eventually it needs to be written many times. So this is pretty inefficient when doing loading data, because loading data is more simple. So we extended to the RocksDB feature to make data loading much faster. So when issuing a write request, then writing to the bottommost, the RocksDB level, the data files directly, and bypassing all the read log and the intermediate level. So by doing so, the write amplification can be just 1, which can be significantly fast to write data. So one requirement is original data must be sorted by primary key to doing that. But our MySQL dump 2 has a feature to dump by primary key. So this is guaranteed. So loading data can be faster when dumping from MyRocks. So this is a bit the steps of the data migration. So creating a table with engine called RocksDB means creating a RocksDB table. Then dropping a secondary indexes, then stopping source slave, then MySQL dump, then order by primary, which is dumping from InnoDB sorted by primary key. Then loading into MyRocks with instructions to using this specific load data, fast data loader feature. After that, order table to adding an index back. So secondary index means that this secondary index creation was also entering the fast data loading first. After that, starting slave. So by doing so in our main database, so we could dump and load into about 1 terabyte InnoDB instance to create a 500 gigabyte, 1 terabyte InnoDB instance to create a 500 gigabyte, the MyRocks instance, in 2 hours or so. So which is pretty good, considering this is an InnoDB database, the MyRocks database. The data verification. So MyRocks and RocksDB is relatively new database technology, so it might have more bugs than was InnoDB. So ensuring data consistency between InnoDB and MyRocks was pretty important to avoid showing conflicting results. So we did a bunch of tests or production verification tests to verify that data is consistent between InnoDB and MyRocks. There are several tests that we did. So first test was checking the index count between primary key and secondary keys. So like this, so select primary key count from a table, the fourth index primary, and union the select from secondary keys. So the single table has multiple secondary keys and primary keys. If the row count of for each index is different, then something is wrong. So the table is corrupted, right? So this is an initial test to check the data is consistent. So and second test is index statistics checks. So my MySQL database as estimated statistics like a row count or index size or primary key size. So if these statistics is significantly different from actual row count, then something is wrong. So we did that test as well. And the third test is a checksumming test between InnoDB. So MySQL has a feature called consistent snapshot. So by starting a transaction with specific global transaction IDs for between the same instance for the starting the transaction from both InnoDB and MyRocks with the same transaction IDs, then subsequent select results should be the same between these two instances. So by starting a transaction at the same time, the same GTID position between InnoDB and MyRocks, then running a select, then comparing the results. If the result is different, then the data is inconsistent. And the fourth part is a shadow test. So MySQL has a feature called the audit plugins, which captures all queries executed in MySQL database. So we captured the select statements, then running the same select statements to both InnoDB and MyRocks with the same transaction snapshot. By doing so, then comparing results, then if results are different, then that something is wrong. So we did a full checksum test to verify the data, the table is consistent, and we also ran the actual queries, the production queries, to compare results between InnoDB and MyRocks. By running these tests, then after passing all of them, then we can safely conclude that MyRocks database is consistent. Another, so shadow traffic test is, can be used at many places. So we have a shadow test framework, so capturing the audit plugins, then deploying them into a multiple MySQL database into master or slaves. So we utilize that feature to running queries on master as well. So running MySQL on master is pretty critical. So we tested that before running MyRocks on master, we ran the shadow queries into a shadow master instance to verify that it would be safe to deploy in master. So we ran that test to find out the number of errors are pretty comparable to InnoDB, or some outstanding errors happening on the gap log, for example. Some incompatible query errors are happening or not. After verifying all of them, so we also started running MyRocks on master. So let me talk about how we created a second MyRocks instance without downtime. So after creating first instance, then creating a second instance is pretty important, because if we have a second instance, then even though you lose one instance, then we can recover from other instance without dump and reload. So dump and load is pretty expensive, but the binary copy is much lightweight. So we have an online backup tool called MyRocks Hot Backup, which is also open source. So by running a MyRocks Hot Backup from one MyRocks slave to other MyRocks slave, then to create a binary, another replica. So this is much faster than dump and load, because this is just as little as just a binary copy. So much lighter overhead. And if losing one of the MyRocks instance, then you can recover from other arrived MyRocks instance by running a MyRocks hot backup. So after creating a second instance, so we have one InnoDB and two InnoDB slaves and two MyRocks slaves. Then next step is promoting MyRocks as a master. So the MySQL, we use a MySQL replication, traditional MySQL replication, which is engine independent. So MyRocks instance can replicate from InnoDB, and after promoting to MyRocks as a master, then the InnoDB slaves can replicate from MyRocks. So this is just simple. So if you know MySQL, so there is a command called a change master statement to promote any instance to master. So the step is simple, but the verification was pretty important. So we did a lot to run shadow testing or correctness testing to verify that it would be safe to promote. So after this is our current state. So we still have InnoDB so that we can promote back InnoDB as a master if MyRocks goes crazy. But so far it's pretty stable. So the final step would be removing InnoDB and overriding with MyRocks. So we are still working in progress about that. Let me talk about crash safety. So crash safety is a pretty important feature from an automation point of view. So if MySQL gets crashed, like crashing or operating system restarts, then how to recover the original MySQL instance? So one typical approach is just copying the entire 1 terabyte or 2 terabyte MySQL instance to another healthy instance. But this is pretty expensive, right? Copying hundreds of gigabytes or terabytes instance is pretty expensive. So what we wanted is if machine can restart, then we just restarting a MySQL process, then it automatically fetching from a master database so that the instance can be consistent. So recovering a MySQL database without recreating the MySQL database is pretty important for us. So this is called a crash safety. So we added this feature. So InnoDB supports crash safety. So we added the same feature in MyRocks as well. So in both the thread crash and the master crash, by restarting the MySQL database, you can recover the data without restoring. And on the master side, the two-phase commit between binary log and write-ahead log is needed to make the crash safe master happen. So we have several ways to make the crash safety work. So depending on the user, the DBA, the MySQL deployment, so there are several ways to do when master crashes. So one approach is, so when master crashes, then wait for a while, then until the machine restarts. Then when machine restarts, then run master, continue to run the instance as a master. So we don't do that, but if you don't have a failover mechanism, then you will eventually need that to prevent data loss. So this is by default MyRocks options. So to do that, you need a full durability so that the machine restarts. You don't want to lose data, right? So in that case, you need a full durability to do that. So the second part is, this is what we are doing in production right now. So we do failover if machine restarts. But if MySQL D process crashes, like a seg fault, then it just wait the MySQL D safe, another angel process, to restarting the MySQL database. So if machine restarts the machine crash, then we immediately promote other threads as a new master. So in that case, you don't need a durability on the original master. But if the angel process may restart the original master and continue to use master, then you need a consistency between binary log and write-ahead log. And the last part is always doing failover. So not many companies do that, I think. But if you can always doing failover, then you don't need any durability on the original master side. Yeah. But we support the several ways depending on the use cases. So anyway, the crash safety is pretty important so that you don't have to rebuild the database on machines, MySQL D crash. Yeah, so notable issues fixed during migrations. We had many errors, like lots of snapshot conflict errors, which was because of the implementation differences between MyRocks and InnoDB. So MyRocks implementation about transaction is pretty close to a Postgres, and the Postgres transaction isolation returning several errors on a repeatable read because of the implementation differences. So we hit these issues in shadow testing. So we changed the default isolation level to read committed to prevent that. And several I/O errors, so we made MyRocks more easier to understand for DBAs, like hanging with I/O errors for 10 minutes or so. It's not so easy to operate, so we changed that. And we have many crash bugs or index statistics bugs during the testing, and we fixed that. The other part is preventing stalls. So InnoDB is pretty robust database, but the MyRocks and RocksDB is pretty new. So one common issue in RocksDB is stalls. So if you write many data to RocksDB database, then it may encounter stalls for blocking for commits for a couple of seconds, so which is pretty problematic for us. So typical write stall is writing many data, like a schema change or migration jobs. So that's why we created a fast data loading feature so that most of the heavy writes can go to the directly into the SSD file and can avoid most of the compactions and the flashes. So, but still, there can be migration jobs that can't insert data by primary key order. So still, we need several ways to preventing stalls. So let me explain about how the stalls can happen. So this is not just for RocksDB, but also applies to any log-structured merge database like Cassandra or HBase. So when write stalls happen means, so basically if you write data too fast, then stalls happen. So estimated number of pending compactions bytes exceeding several bytes. In MyRocks, it's 64 gigabytes by default. But if you estimate, RocksDB estimates that writing too much, then it's slowing down. And the number of L0, the highest level, has the number of files exceeded some threshold, 10 files, then it slows down. And the number of unflashed mem tables, so the flashing to SSD files cannot keep up with the write speed, then it slows down. And all of the incidents are written to a log file, so we can detect that. So writing to log is very important for diagnostics purposes. And what happens on write stores is we have two stores. One is a soft store, so slowing down. So in MyRocks, the commit taking longer than usual. So the total estimated bytes written to a mem table is capped to a delayed write rate, which is 60 megabytes by default. So slowing down the commit speed, then so that the compactions can be faster than write ingestion speed. And if the soft store cannot keep up, then hard store happens, then blocking all writes, then until the compaction finishes. So which is really bad. So we spend a lot of time to prevent both soft stores and hard stores. So there are several tips to mitigating stores. So one is speeding up compactions, so using a faster compression algorithm. So we use LZ4 for higher levels, and we use G standard, which is a newer compression algorithm, which is also space efficient in the bottommost level, and increasing the background compaction rates so that compaction can be faster. And reducing the total bytes written is writing less, so making compactions more efficient to write less to storage. And another interesting issue on Flash is deleting files. So if you delete files too fast, delete too many files too fast, then this causes a problem of the trim stores. So the compactions reads the 10 files, then writing 10 files, then deleting 10 files. If we delete files too fast, then trim stores happen. So we change the behavior by deleting slowly so that trim stores don't happen on Flash. So MyRocks throttles the SSD file deletes by 60 megabytes by default, so that the huge deletion can't happen immediately. Okay, the last part is monitoring. So there are several ways to monitor MyRocks activities, MyRocks files, or several commands, and several tables for diagnostic purposes. So let me explain about two commands. One is the show engine RocksDB status, which is a SQL command to monitor the activities like column families, database size, or how many bytes written, or compactions efficiencies. So this SQL interface is pretty useful for operating RocksDB. And we also supported status counters, which is supported by InnoDB as well. So how many rows are inserted or deleted per second. Yeah, so this is the last slide. So summary, so we started migrating from InnoDB to MyRocks in our main database. So we run both master and slaves in production. So our major motivation was to save space. Saving space by half and consolidating machines and freeing up about half machines was a big motivation. And we did a bunch of tests, and the one big, most contributing test was data correctness check. So by verifying data consistency between InnoDB and MyRocks, we could confidently deploy MyRocks in production. And preventing stores like bulk loading was very helpful. And we supported transactions so that it can be crash safe. So that's all. Thank you very much.